As the world economy and population develops rapidly, the waste-activated sludge production from sewage treatment plants increased significantly. However, the available methods used to manage waste have shortcomings that could not be overcome. So what is the best way to manage this sludge efficiently? Good day everyone, welcome to the Journal Review video. First, let me introduce myself and my groupmate. My name is Yue Min and here is my groupmate Farhana, Danial, Syahiqah and Najwa. And we are the members from Lecture Group 3, Subgroup 2. Today we would like to review a research paper titled An Integrated Approach for Waste-Activated Sludge Management Towards Electric Energy Production or Resource Reuse by the author Sing Hong He and Chiu in 2019. Here is the introduction part. The current study of the sludge management focuses on how to achieve resource recovery as the waste contain high organic matter fraction. However, the anaerobic biological process, which is so far the efficient method, can only convert 30 to 35% of total organic substances in sludge into biomethane by anaerobic fermentation. The remaining 70% organics are treated by conventional methods such as landfill incineration, which increase environmental burden. Therefore, this study aimed to develop an integrated approach for waste management toward electric energy harvest or resource reuse with zero solid discharge. Prior to anaerobic fermentation, waste solubilization was increased by enzymatic pretreatment for enhancing anaerobic acidogenesis performance. After solid-liquid separation, the fermentation broth was fed into microbial fuel cells for electric energy production, while the solid residue was used as a replacement material for making cements. It was expected that this study might shed light on the total solution of future waste management towards bioenergy recovery or resource reuse.
The next part is materials and methods. The first method is waste enzyme characteristic and enzymatic pretreatment. The waste-activated sludge was collected from secondary tank of a full-scale WWTP with comprehensive properties as shown in Table 1. The methods for preparation and characteristic of the hydrolytic enzymes mixture used in this study were shown in Table 2. The enzymatic pretreatment was implemented by water bath at 37 ± 0.2 degrees Celsius for 3 hours, where the proportional of individual enzyme in the enzyme mixture was maintained at the following mass ratio. The second method is anaerobic fermentation MFC device and operations. 2 cylindrical anaerobic bioreactors were designed to conduct the waste batch fermentation, and 1 bioreactor was operated as the control group which fed with fresh waste. The fermentation system was stirred by a blender, and the condition was strictly maintained by using a water-safe unit on the bioreactor to inhibit the airflow. The bioreactors fed with pre-treated waste were operated for 10 days in order to achieve volatile fatty acid VFA accumulation. After the fermentation, the liquid and solid residues were separated for the next experiments. The electrogenesis was conducted by using cylinder-type air cathode single-chamber MFCs, where it contained a plain carbon cloth-made air cathode of 1.5 cm in semi-diameter and an anode from a carbon brush with surface area of 7.8 cm². Its effective working volume was 28 ml. Meanwhile, the external circuit was from the cathode to the anode by titanium wire with external resistor of 500 ohms. A data acquisition card, which is linked to a computer for data recording at a time interval of 1 second, was used to monitor the voltage of MFCs. The next method is analysis method, and it was divided into 2 parts. The first part is general analysis, where the following were analyzed, including the soluble chemical oxygen demand, total solid, volatile solid, soluble protein, the soluble carbohydrate, the pH value, the VFA concentration, the voltage output from MFC, and lastly, the chemical composition of sludge. These parameters were measured by using their respective analysis tools. The second part is data analysis. The current density was obtained based on the following equation. Next, the power density was calculated as follows. The power density curves was determined where the corresponding current density and power density were calculated, and the power density curve was constructed by plotting power density against the current density. Meanwhile, the electric energy conversion efficiency by MFC can be calculated by using this equation. Lastly, the theoretical electricity generation efficiency TEGE through maintained combustion can be determined with the following formula. For the final method, the microbial community analysis was done where the DNA extraction of anodic biofilm sample in the MFC was performed. The 16 srRNA gene fragment containing V3, V4 regions were amplified using the primer pair 341F and S05R. Then the PCR products were purified and sent for sequencing. The taxonomy of the species was determined based on the OTUs obtained by the RDP classifier.
The next part is result and discussion.
The enzymatic pretreatment that was subjected to the waste-activated sludges increased their solubilization and in the same time surged the amount of soluble chemical oxygen demand within a short period of time. Also, the mixed enzymes catalysis that occurred in this process also plays a huge role in degrading the macromolecules of the extracellular polymerase substances and lysing the microbial cells in the waste-activated sludges. In the same time, these two breakdown processes also enhance the anaerobic acidogenesis by increasing the accumulation of volatile fatty acids, which is 2.53 times higher than volatile fatty acids accumulated by the control group. As a result, the increase of volatile fatty acids elevated the solubilization of the waste-activated sludge. Enzymatic pretreatment is proven to be more efficient as it increases the production of volatile fatty acids and methane in a short amount of time. The preparation of the enzymes only need a small cost as the source for the enzyme is easy to obtain. After the treatment is done, the enzymes can be degraded without causing any damage to the environment. After the microbial fuel cells were fed using fermentation liquid from enzymolysis pretreated waste-activated sludge, the output voltage from the microbial fuel cells gradually stabilized at 0.64 volts after 18 days of operation with the maximum power of 0.184 watt per meter square. By feeding the fermentation liquid to the microbial fuel cells, the efficiency of the electric energy conversion rises up to 1.254 kWh per kilogram, and this conversion is about 91.4% of the energy converted via methane combustion. Although it is slightly lower than methane combustion, this shows that a relatively high electric energy can be obtained from the fermentation broth. The residues of the enzyme treatment, fermentation and sintering contains a big amount of silica, alumina, calcium oxide and iron oxide. These residues can be incinerated and later will be used in making cement components. It is pointed out by researchers that up to 30% of the cement composites can be replaced by inorganic waste from waste-activated sludge, and this shows that the importance of waste-activated sludge in the future.
For part 3.3, describe about total solution scenario for waste-activated sludge management in situ of wastewater treatment plant. The figure 4 shows an integrated waste-activated sludge management approach towards electric energy and resource reuse.
For the aspect of energy or resource output, the 14.86 gram of waste-activated sludge in this study was able to generate about 4.5 times 10 to the power of -3 kilowatt-hour of electricity with 3.1 gram of inorganic matters as the replacement of cement composites after sintering.
In terms of economic evaluation, the major treatment cost of this approach was focused on enzymatic pretreatment. In addition, the electric obtained via microbial fuel cells by the in-situ produced waste-activated sludge was 51.3% of total electric energy consumed potentially, which means over half of electric energy consumed in wastewater treatment plant could be recovered in this study.
Lastly, for the conclusion and reflection part.
An innovative and potential approach for managing waste-activated sludge into creating useful resources such as electrical energy as well as zero secondary waste discharge is shown to be achieved in this study. To brief, the process goes through pre-treatments by enzymolysis based on anaerobic fermentation and microbial fuel cells. Waste-activated sludge undergoes solubilization by the 3-hour enzymatic pretreatment, which prompted volatile fatty acid production. The enzymatic pretreatment for boosting organic waste biodegradability and bioconversion showed incomparable advantages, one of them being the high solubilization efficiency with enhancing organic matters bioconversion via anaerobic fermentation, and this is increasing methane production with less operation time. The other is the enzyme's source was brought with very low purchase or preparation cost. There is no need of extra energy or reagents consumption. The enzymes could be rapidly degraded without causing extra environmental burden. After solid-liquid separation, fermentation liquid with high volatile fatty acid content was fed into microbial fuel cells for electric energy production, while the solid residues were used for making building materials such as blended cements. However, the drawback is some potential risk would emerge if the waste-activated sludge fermentation treatment process upscaling such as bioconversion efficiency would decrease. Though, this devises a great possibility of a normal collocation conception by collocating wastewater treatment of wastewater treatment plants and discharge waste-activated sludge via anaerobic fermentation followed with microbial fuel cells for achieving self-sustainable wastewater treatment to a great extent. Co-locating concept offers new insights into future waste-activated sludge management and wastewater treatment with the goals to energy neutral and resource reuse.